Assalamu alaikum, dear students. We're back with another video lesson. In the previous lesson, we talked about rotational motion, and of course, we've solved so many questions in that regard. And then, of course, we ended up solving some other questions related to the torque as well. Today, we'll continue solving some more questions related to rotational equilibrium and torque. And then, of course, after that, we'll go to a new concept. Okay, so today we're going to solve this question. Take a look carefully. It says what? We have a 12 kilogram mass that is attached to a cord which is wrapped around a wheel with a radius of 10 centimeters. Don't forget. As shown in the figure 2.17, which you see over there, the acceleration of the mass down the frictionless incline is measured to be 2 meters per second squared. Assuming the axle of the wheel to be frictionless, determine the force in the rope. That'll be the tension, of course. And then after that, the moment of inertia of the wheel. And then part C, the angular speed of the wheel 2 seconds after it begins rotating, starting from rest. So how are you going to solve questions like this? By the way, the diagram will be given, or this figure. So what are the things you have? You have acceleration downward, okay? So you have F tension. There is, of course, a wheel. And you can see this mass attached to the rope, which is attached, or it is on the wheel. So this mass is going downward. You can see the angle of the incline or the slope with the horizontal is 37 degrees. Okay, so remember, you have mass, the information that are given, you have mass, you have radius, and of course you have acceleration. So the things you need to find are tension in the rope, okay, and of course later on moment of inertia of the wheel, and then angular or final angular speed. Okay, so let's begin with bringing a rectangle so we can solve all these questions together. Bear with me, okay? Maybe perhaps I can redraw this one for you one more time just so that you know how it is done, okay? Or what are the forces, so it will be very obvious to you, or what exactly we're doing here. So there is an incline, you can say, okay? There is 37 degrees with a horizontal. There is a wheel that is here, and of course there is a box or a mass that is attached to the wheel, which is 12 kilogram, and there is a downward acceleration of 2 meters per second squared. Okay, so on the radius of the wheel the radius here is 10 centimeter, and of course you already know that you need to convert 10 centimeter into meter. Okay, so what are we required to find? We're required to find the tension in the rope, which is, you can call it Ft in here. Okay, so I want you to know one thing before we begin here. Okay, there is a force, you can say, that is downward. That is because of the tension, okay? And of course, there is an upward force, which is the tension in the rope, of course. It tries to hold the mass from not going down, okay? But the mass is still, or you can say there is another force which is called force of gravity, which is bigger than the force in the rope. So of course, this is another reason why this mass is going downward with an acceleration of 2 meters per second squared. But we've already learned that this mass, there is, if the mass is 12, we know that there is a gravitational force, or this gravitational force, you can call it mg, correct? Okay, but then this mg, because it is not, let's say, perpendicular to the horizontal, you can say, there is an angle here. So of course we're going to analyze this force or gravitational force into two components. So one of the component will be mg cosine theta, right? That is going to be the weight of the object, of course. And then the other side here is going to be mg, right, sine theta. This mg sine theta, of course, it is the gravitational force on x-axis. You can say gravitational force on y-axis. So this one you can say Fg on x if you would like to call it, and this is Fgy. Do you know that there is a normal force here, Fn? These two are on the same line, so this of course will cancel each other out. So these two forces have no effect, okay? Well, this one is the force of gravity, is what is pulling the box downward with an acceleration of 2 meters per second squared. Okay, so in another word, there are two forces. One of the forces that is acting downward, that is Fg, And then there is another force which is upward, that is Ft. The resultant of this two, or you can say the effect of this two, gives this box an acceleration of 2 meters per second square. So based on what? Based on Newton's second law of motion, of course, we have what? If you know, yes? We have F net, you can say, right? That is for translational motion, equals to why translational motion? Because the object moves in a straight line. We're not talking about the wheel yet, so keep that in mind. So F net equals to what? Equals to mass times acceleration, yes? But this is not the force, this is the net force. So how many forces do we have? There are two forces, yes? So what are these two forces? Of course, one of them is Fg, right? Fg, that would be gravitational force pulling down on the box, and this is why it moves downward, which is bigger than the tension force, okay? If tension force was bigger, then of course the box would be moving or sliding upward, okay? So Fg minus Ft equals to mass times acceleration. But what do we have instead of Fg? We don't have Fg directly, so you're going to go with mg, that is mass times gravitational acceleration times sine theta. We have an angle. This is why we're going to use this. So mg sine theta. What is theta? Let's go with sine theta first, equals to F tangent, or minus F tangent first, not equal to yet, okay? Let's not rush. F tangent equals to mass times acceleration, okay? So we want F tangent, so can I move this one to the other side? Let me use a different color, so I'll take Ft to the other side, and of course I'll bring Ma to this side. So I can say mg, right, sine theta minus Ma, or you can substitute numbers, then you can do this, this step, okay, and then equals to Ft. Okay, by the way, it is negative if it goes to the other side, it becomes positive. This positive, if it comes to the other side or to this side, it becomes negative. Now, all you need to do is to find Ft, you just have to substitute numbers, and then you can find Ft. So let's find Ft. Are you still with me? Very good. Okay. Let's use a different color. So what is the mass of the box? That is 12, yes? So remember, mg sine theta minus mass times the acceleration. So we can say 12 times what? 9.81. Excellent. Multiplied by sine, what is the angle? 37. These are all Fg, don't forget. Minus, right? Minus what? Minus mass times the acceleration. Again, the mass is 12, the acceleration is 2. All this equals to F tangent, or the tangent and the force. Let's separate the two so that, okay. So now, use your calculator, multiply this, and find the answer for me. So let's get a calculator. So the numbers that we have is 12, okay? 12 multiplied by what? By 9.81 multiplied by sine 37 degrees. Then you can close bracket and minus open bracket 12 times 2. Okay, because our acceleration is 2 meters per second squared. So the answer will be 46.8, yeah? Okay, so we can say F tangent is 46.8. We can round it up to 47. That is also fine. That is the tangent force in the rope. That is the first part of the answer. Now, what is the second part? The moment of inertia of the wheel. Okay, now here comes another part. Remember, moment of inertia of the wheel. So what is the moment of inertia of a wheel? Or first of all, what is the equation for, let's say, for the moment of inertia and of course of a wheel as well? So you already know that. For a wheel, moment of inertia, or is there any other ways where we can do that? Can we use 1/2? I mean, not that, because we're given the force, yes? So because we have this, we can say moment of inertia of a wheel. By the way, because there is a rotation, so you have the net torque, yeah? Or net equals to what? Equals to mass or moment of inertia times angular acceleration. Can we say angular acceleration? Yes, very good. But do we have angular acceleration? No. So how are you going to find angular acceleration? Angular acceleration equals to, we can do all this in one step perhaps. Okay, so angular acceleration equals to tangential acceleration over the radius, yeah? And then here's moment of inertia. And then what about the net torque? What is the net torque equal to? Isn't this equal to the net torque equals to force, where you can say F tangent, because that would be tangent to the wheel, or just normally F tangent multiplied by the radius of the wheel. Or you could just say force times the distance, but what would be the distance here? The distance will be the radius of the wheel. So what we're talking about is this. This force is acting tangentially on the wheel, of course, which makes it rotate. So this is the force, and this is the radius, or you can call it the distance. So what is the force that we have? The force is 47 Newton multiplied by 10 centimeter. Now, we said we're not going to use 10 centimeter. You'll have to use meters. So how do you convert 10 centimeter to meter? Divided by 100. Or if we, like do this directly, we'll just say multiply by 0.1. How do we get 0.1? That is 10 divided by 100. Very good. And then moment of inertia again equals to, or multiplied by, what is the acceleration that we have? The acceleration is 2, that is tangential acceleration, once again divided by the radius, which is 0.1. Okay, so 47 multiplied by 0.1, that is going to be 4.7 equals to moment of inertia multiplied by 2 divided by 0.1, that is 20. So how do you find I? Divide both sides by 20, yeah? Or just take 20 or bring it here, okay? That's the same thing. So moment of inertia of the wheel, don't forget, equals to 4.7 divided by 20. So what is 4.7 divided by 20? 4.7 divided by 20, the answer will be 23, as a matter of fact, is you can say 2.35 times 10 to the power negative 1, or simply 0.235. And because it is moment of inertia, it is going to be kilogram meter squared. And this is the answer. Let's circle the answer or put it in a rectangle. Now, this is how you're going to find the moment of inertia of the wheel. Now, we're at the last part of this question. It says, part C, the angular speed of what? Of the wheel is 2, let's say of the wheel, 2 seconds after it began rotating, starting from rest. So how do you find the angular speed, yeah? That's very simple. Perhaps you can save some space here. So we know that, listen, we have initial, what was the initial, sorry, my bad. Okay, it says after it begins rotating, yeah, starting from rest. If it starts from rest, that means omega initial is 0. Very good. Now, what about final? It says find the final, yeah? So omega final, it is unknown, so we're been asked to find this. What about the time? The time is basically 2 seconds, and that is delta t. Okay, let's make it small this. So, you tell me, will you be able to find omega final? Yes. Do you remember the equations, the 4 equations of motion? Remember, in rotational motion here. So, omega final equals to omega initial, yes, plus angular acceleration multiplied by t or delta t. Okay, so let's go with delta t in this case. Delta t. All right, so omega final, it tells you that it is 0, plus the angular acceleration. What was the angular acceleration, by the way? We found it before, yeah? The angular acceleration here, where was it? Here. Or if not, we can do it here, yeah? Angular acceleration, we found it, by the way. Angular acceleration, that is tangential divided by the radius. 2 divided by 0.1, that is 20. If not, you could do it again. 2 divided by the radius 0.1, that is basically 20. So in this case, 20 multiplied by 2, and of course, you tell me what is the answer. So we can say omega final equals to 50, but 50 what? Minus 10. That is equal to 40, yes? Excellent. And what is the unit of omega final? That is radian per second square. No, just second. Well done. All right, so I hope the idea is clear. If you were following from the beginning, of course you would know where I have started. So otherwise, if you just started looking at this, of course it looks a little bit messy. And I hope you started earlier. So as you can see here are the answers, very well organized. So we said by rounding that would be 47. We found the moment of inertia, which was, or before that you can find the angular acceleration, that was 20 radian per second squared. And then after that we found the torque, which was 0.235. I took 3 digits. And then to find the omega final, of course, that was 40 radian per second. Okay, or we use this equation, Newton's, let's say, 4 equations of motion. The first one you can say based on my, let's say, arrangement. Okay, now we have another question, which is also very interesting. Bear with me here. This is also interesting. It says, the combination of an applied force and friction force produces a constant, don't forget this, constant torque of 36 Newton meter. On a wheel, remember, so we have a wheel, yeah? So remember, whenever you see a shape or gives you a name, always remember the moment. Then it says, on a wheel rotating about a fixed axis, so the applied force acts for 6 seconds. That is the force, during which time angular speed of the wheel increases from. So the angular speed increases from what? From 0 to 12. Oh, it doesn't write? All right, let's get it back. So from 0 to 12. So this is initial, 12 is omega final. That is this. Then the applied force is then removed. What happens if the applied force is then removed, okay? Or is it removed? The wheel comes to rest. So, but at what angular speed will it come to rest? It comes from 12 to 0. So can I say after the force is removed, 12 would be the initial, forget it. Just stay with me. Let's organize this, turn this to something interesting. But before this, okay, we have 36. Keep that number in mind. Let's get this done. Okay. So we have, what do we have? We have 36, that is a constant torque, yeah? So we can say we have a constant torque of 36. Okay, so we have a torque of 36 Newton meter. Don't forget this. Okay, it says on a wheel that is on this, so we have delta t, which is 6.0 or just 6 seconds. Okay, next is during which time during which time the angular speed of the wheel increases from, so we can say omega initial is 0, omega final is, it increases to 12 radian per second. So can we call this one speeding up? Excellent. And then the next thing says the applied force is then removed and the wheel comes to rest. Now remember this, whenever it says the applied force is removed, that means it's going to slow down, of course, because of friction, yes? So we can say, it says until it comes to rest. When it says it comes to rest, that means final angular speed will be 0. Excellent. But what about initial angular speed? It was speeding up to 12, yeah? From 12, it starts to slow down. So can I say 12 is the initial angular speed? Excellent. So these are radian per second, yes? Very good. Next thing it says, the wheel comes to rest in, by the way, so it comes to rest in a time of 65 seconds. Don't forget. So answer the following questions. The first one, it says, what is the moment of inertia of the wheel? How do you find the moment of inertia of a wheel? But don't forget this, guys, okay? Because the moment of inertia of the wheel is always constant, okay? So once you find the moment of inertia of the wheel, it doesn't change unless something happens to the wheel that can change either the mass of the wheel or the radius of the wheel, which in this case, none of these will happen. So how are you going to find the moment of inertia of the wheel, guys? Easy enough, yeah? So take a look, moment of inertia of a wheel equals to what? So let's say moment of inertia, I of a wheel equals to what? So we know that the net torque equals to moment of inertia multiplied by the angular acceleration, correct? But here's the thing, do we have angular acceleration? No. Can we find it? Yes, because we have final, initial, and delta t. What about the net torque? I already have it, so can I find the moment of inertia? Yes, but how about if I find the angular acceleration first? Okay, so for angular acceleration, let me just plug in some numbers. So for this one, that is going to be, or for net, let's start with this. This is 36, right, equals to moment of inertia multiplied by, for angular acceleration equal to omega final, okay? Let's write it, minus omega initial divided by delta t. So let's write one more step. 36 equals to moment of inertia multiplied by omega final is 12 minus 0 divided by the delta t, which is 6 seconds. Okay, so 12 divided by 6, that is 2. You can take it to the other side under 36 or divide both sides by 2. In this case, moment of inertia equals to 18, and that is kilogram meter squared. By the way, moment of inertia doesn't change because it is the same wheel, whether if it is speeding up or slowing down. Okay, that is the moment of inertia, and that is the answer for part A. Now, the second part says, what is the frictional torque? Now, of course, after you remove the force, the wheel is going to slow down because of friction. So what is the torque of, or the torque of friction, or the frictional torque, you can say, that is applied on the wheel, which makes the wheel to slow down and stop eventually. So we can say, in order to find this one, we're going to use this, all right? Once again, we'll use the equation that we have, but this time we don't have the torque. We're not going to use this torque. Why? Because this torque was for speeding up, guys. Okay, now the next one here, we can say torque of friction, right, equals to moment of inertia multiplied by angular acceleration. Multiplied by angular acceleration. Now, here's the frictional torque is that what we're going to find. And then moment of inertia of the wheel is going to be the same, which is 18. How about the angular acceleration? Am I going to use this? Absolutely not. Do you know why? Because this angular acceleration was for speeding up. Now, here it is going to slow down from 12 to 0 in 65 seconds. So, in this case, we're going to use the net torque, or of friction, let's say, equals to moment of inertia, which is 18. Don't forget, it is going to be final. What is final? 0. Minus. What is initial? 12. Divided by. What is the time? 65 seconds. And of course, the answer to all this equals to 18 multiplied by the way, 0 minus 12, that is negative 12 divided by 65, it is going to be negative 0.18 if I'm not mistaken, yes? I can use a calculator. All right, so let's double check with the number. Negative 12 divided by 65. And of course, the answer is, yes, 0.185. 185. Let me add 5 to this one as well. Okay, 185. Can I round it to 19? Yes, that is also possible. So now all you need to do is just multiply. So 18 multiplied by negative 0.185. 0.185. The answer is going to be negative 3.3, okay? 0.33. So the net torque here, or torque of friction, perhaps I can write it up, okay? Let's see. So we can say torque of friction is going to be negative 3.33. And of course, you know, the unit of the torque is, which is Newton meter. All right. So negative 3.3. Okay, now that is the answer to the second part. What about the last part? The last part says, how many revolutions does the wheel make during the entire 71 second time interval? Now that is very interesting, and you need to pay close attention to this. It doesn't says, it says how many revolutions here. So we want delta theta, right? But not in radian. It has to be in revolution. So how are you going to find this one here? Well, simple enough. All right, bear with me. Let me erase these. And then, of course, we'll do this part as well. All right. So by the way, we can do all this in one step. I'll try to break it down so you can understand and you can follow me. And then once you fully understand, then of course we can go with one step as well. So for delta theta, remember this, okay? Delta theta, you already know that, one of the Newton's law of motion, okay? Or one of the four equations. We have 1 over 2, that is for speeding up, don't forget. Omega initial plus omega final multiplied by delta t. All right, but remember the angle that you're getting here, it is going to be in radian. So 1 over 2 multiplied by, we said omega initial was 0, final was 12. That is in case of, or in the case of speeding up, don't forget. Right? Or you can say speeding up, okay? So multiplied by delta t, and it was speeding up for, let's say, 6 seconds, all right? Multiplied by 6 seconds. So 12, or just 6 divided by 2, that is going to be 3. 3 times 12, it is going to be 36 radian. Don't forget this. That is in terms of speeding up. What about in terms of slowing down? We'll use the same equation. So we'll say delta theta this time equals to, all right, delta theta, that is for slowing down. It is still in radian, by the way, equals to 1 over 2 omega initial plus omega final multiplied by delta t, which is going to be, delta theta is going to be what? Is going to be 1 over 2. Omega initial was 12 plus final was 0 multiplied by 65 seconds, guys. That is for the second part, okay? It says then it'll remove the wheel to whatever in 65 seconds. Okay, so now 12 divided by 2, that is going to be 6. 6 times 65, you can say, yeah? 6 times 65, or you could do the whole thing here. And of course, we will get 390. 390 what? By the way, we can call this one delta theta 1. We can call this one delta theta 2. So delta theta 2 equals to 390 radian. But look again, we want the angle in revolutions. So how are you going to find this? How about we find the total angle in radian or displacement, and then we can convert it, yes? Okay, moving on. So we can say delta theta, that would be total, equal to delta or theta, delta theta 1 plus delta theta 2. These are angular displacement, by the way, yes? So 36 plus 390. And that is 426, yes? 426 radian. But you know that. How do we convert radian to revolutions? Divided by, or divide this by 2 pi, yes? Divide this by 2 pi, because each, or you can say 360 or whatever, or just divide by 2 pi. Remember, 360 equal to 1 revolution, yeah? By the way, these are in radian, yeah? So if it is in radian, we just divide it by 2 pi, because you can see that, what was the thing, yeah? 2 pi equal to 1 revolution. So we just divide this one by 2 pi, okay? And then, of course, you will find, or the answer will be the number of revolutions. So 426 divided by 2 pi, we will get 67.8 revs, yeah? Or we can round it up to 68 revolutions as well. So this is the total number of revolutions, okay? Revolutions, yes? So this would be the answer to the last part. Okay, so I hope you understood this. If not, please go back to the beginning of the question and watch this again, okay? And you can see here, once again, first of all, you'll have to find moment of inertia, which we found. It was 18 kilogram. That was the case of, in the case of speeding up, of course. And then in the case of slowing down, we use the same moment of inertia, but then we use the deceleration here, which was negative 1.8. I used 1.85, okay, which is you get a negative 3.3, which is the same answer. Then we want the total, right, angular displacement by an revolution. So first we find the angular displacement for both cases, for speeding up or slowing down. Once you find the total, then divide by 2 pi. You'll get the number of revolution, which is 67.8, or by rounding, we can just go with 68. All right, moving on to the next question. We have this question here. It says, a cable passes over a pulley here. But remember, it's not just a pulley. You can see that there are two forces from each side of the pulley. That the pulley that rotates about a fixed axis, and that is how it is. Because of friction, the force in the cable is not the same on both, or let's say on opposite sides of the pulley. The force on one side, so the force that we have on one side is 120. So we can say this force on one side is 120. And the force on the other side is 100 Newton, yeah? So this is 100, 120, 100 Newton, okay? Assuming that the pulley is a uniform disc, remember, what is the moment of inertia of a pulley or of a disc? Yeah? Moment of inertia, that is 1/2 of a disc. Mass times radius squared, you will need this. Okay, with a massive, so the mass is 2.1 kilogram, and a radius of, so this radius is 0.81. Determine the angular acceleration of the pulley. Yes, how do you find the angular acceleration of the pulley? Now this could be very easy, and also it could be very confusing at the same time, so you better pay attention, and then so you can understand well. Okay, let me not cover this diagram here. Okay, so here's what we have. We have a pulley, right? Remember, we have two forces on each side, 120, 100. These are in Newton, and of course we have mass of the pulley and radius of the pulley. So we can say F1 is, F1, okay, let me write it nicer. F1 is 120 Newton, F2 is 100 Newton, and then the radius is, what was the radius? Where? Okay, somebody help me find it. Yes, it is 0.81 Newton, meter, not what Newton you're talking about. Okay, that is this, 0.81 meter, and then the mass of the pulley is 2.1 kilogram. So find what? Find the angular acceleration. Okay, find the angular acceleration of the pulley. There we go. Take a look. By the way, we already know that each one of these forces apply a, let's say, a torque on the object trying to turn this pulley. Okay, one of them here, there is a distance, of course, which is the radius. These two radiuses are the same for both. So this force try to, let's say, rotate the pulley this way, or let's say counterclockwise, and then this force here, or this way, try to rotate the pulley clockwise, yes? But of course this is bigger, so it's going to rotate the otherwise, counterclockwise, but with what angular acceleration? So because we have two forces that are in, let's say, they try to turn or rotate the pulley in, let's say, in opposite direction, here's what we're going to do. The main equation is the net torque will be, all right, equal to what? Equal to moment of inertia multiplied by angular acceleration. But what is the net here? Remember, we have two, right, forces. Each one of them tries to rotate or turn the pulley in opposite direction. So are we going to combine them? No, we're going to subtract them. Very good, very good. But remember, not just their forces, with multiplying force with the distance gives us the torque, yeah? Because 120 is bigger, we'll go with that first. Or we can say F1 multiplied by distance, or the radius in this case, minus, right, that is the first torque, or the torque that is produced by the first force. Second force multiplied by the radius, okay, and that is the second torque equal to moment of inertia multiplied by the angular acceleration. How about if I use this as well, right? For the angular acceleration of a disk, we have 1/2 mass times the radius squared. I'll use capital R, okay? But the same as, actually, let's use R small so that you don't say, Mr. why aren't you using the same thing? And then multiplied by the angular acceleration. We're trying to find this guy. Okay, so how about we do this first? F1, that is 120. Let me use a different color. 120 multiplied by the radius. What is the radius again? It is 0.81 meter. 0.81 meter. Put it in a bracket. Minus F2, that is 100, multiplied by the same radius, 0.81, because it's the same, is equal to 1 over 2. What is the mass of the pulley? It is 2.1 kilogram. Let's use a cross or times 2.1 kilogram. Are you with me? Very good. And then multiply by the radius square, which is 0.81. These are 0. I hope you can see. 0.81 squared. No. Should have used a bigger space, but still, I hope you can see well. Okay, so this is 1 over 2 multiplied by the mass, which is 2.1 multiplied by the radius, which is 0.81 squared multiplied by the acceleration. So, use a calculator. 120 multiplied by 0.81, and then minus, yeah? We can do all this in one step. So you can open a bracket if you're using a calculator so that you don't get a different answer. Multiplied by 0.81, okay? And then close bracket, and then minus, open another bracket, 100 multiplied by 0.81, close bracket equal, or press equal, you will get 16.2. 16.2 equals 2. Now, 1 over 2 multiplied by 1 over 2, it is 0.5, yes? Very good. Multiplied by 2.1, that is the mass, multiplied by the radius squared, don't forget, which is 0.81 squared, yes? And then this equals to 0.689. We can say 69 by rounding, okay? And then multiplied by the angular acceleration. So how do you find angular acceleration now? Simple, yes? Divide both sides. Angular acceleration equals to 16.2 divided by 0.69. 0.69. So of course now the answer will be 16.2 divided by 0.69. The answer will be 23.5. What a nice number, 23.5. And remember, what is the unit? This is angular acceleration, so it's going to be radian per second squared. Let me write this square nicer. Voila. All right, so I hope you understood how it is done, all right? The key idea here is how to subtract this two. Like these forces try to rotate the pulley in different or opposite direction. So of course we will multiply each one of these to the radius to get a torque, and we subtract them because they try to turn the pulley counter, let's say in opposite directions. All right, moving on to a few Zhyar questions. These Zhyar questions are very similar to the questions that we have solved so far. The first one, perhaps, let me see. I think I'm not going to do them for you. I'll leave this as a homework, but I'll just go through it to see if there is anything that I need to inform you about. The combination of the applied force and the frictional torque produce a constant. This is very similar to what we have, like just went through the in the other question, yeah, the one before the last. Okay, Newton meter on a wheel rotating this. So the applied force, or the force applied force acts for 6 seconds. During this time, the angular speed of the wheel increases from 0 to 12 radian per second. Right, then the applied force removed, the wheel comes to rest in 65 seconds. What is the frictional torque? So first of all, you're going to find the moment of inertia, all right, by using the net torque, by using the angular acceleration. Then you'll use the torque, or not my bad, you'll use the moment of inertia to find the torque of friction, which is very similar to this question, except then for the last part, yeah? So you're going to do exactly this, but different numbers, of course, yeah? So, but there is no this part in that question here. Okay. So that was for question 1. And then the answer, of course, it has to be 3.3 in this case. All right, as for question 2, says a 350 kilogram merry-go-round in the shape of a horizontal disc. Remember, whenever you see a disc, and of course there is merry-go, that means there is rotation. Whenever there's rotation and there is a disk shape, remember you have moment of inertia, and of course if it is for disk, that is 1 over 2 mr squared. Don't forget this. All right, this says the radius is 1.5. It's set in motion by wrapping a rope about the rim of the disk and pulling on the rope. How large the torque would have to be exerted to bring the merry-go-round from rest, that means omega initial is 0, and then to an angular speed of 3.14 radian per second, that is omega final, right? And then this is delta t in 2 seconds. So here we have the angular acceleration, yes? And you have a disk, so moment of inertia of a disk is 1 over 2 r squared. Find the net torque. It says find what? How large the torque would be. I'll write the equation for you, but I'm not going to solve it, yeah? So you can do this, or the rest is on you. So we can say the net torque in here, right, equals to moment of inertia multiplied by the angular acceleration. Once again, the net torque equals to moment of inertia of a disk is going to be 1 over 2 mr squared multiplied by the angular acceleration, that is final minus initial, divided by delta t. You plug in the numbers, and of course you'll get one of these options, and then you can choose that. Again, this would be your homework, or there's 2 questions. All right, now we are at a new concept, but I believe it would be best if I think we'll just go ahead with this. Okay, now we have angular momentum. What is angular momentum? Okay, remember, angular, previously, or in grade 11, you can say, you've studied about momentum. And what was momentum? Simply, momentum is the product of mass times velocity. Okay, if I take you, let's say, to this. So you've studied about momentum in grade 11. Momentum was mass times velocity. And of course, momentum was a vector, correct? It could be, let's say, and it was the momentum, you can say it is, could be to the right, could be to the left, could be positive, could be negative as well. And this is the mass, of course. Okay, and here, right, in grade 12, of course, we're going to use, instead of momentum, we have angular momentum. And angular momentum is represented by capital letter L, okay? And then, of course, instead of mass, we can say, what have we used so far instead of mass? Of course, instead of using inertia, let's say, we're going to use moment of inertia. Yeah? So instead of mass, we're going to use I, that is moment of inertia. And guess what? What do we use instead of speed or velocity? We will use angular velocity, and that is as simple as this. So angular momentum equals to moment of inertia, or is, how can we define this, by the way? We can say angular momentum. It's not just the momentum, it is angular, because we're studying rotational motion. That would be the product of the moment of inertia and then with the angular speed of the object. And of course, that would be rotating about a fixed axis or an axis. How about the unit of, let's say, moment of inertia? Yes? Or angular momentum, not moment of inertia. Of course, what is the unit of this? Yeah? Do you remember the unit of this? So the unit of angular momentum, we can say it is, for this one it was kilogram meter squared, and then for the angular momentum it was radian per second here, but we're not going to use the second, so it will be just multiplied by let's say 1 over second squared, or you could just say kilogram meter squared divided by second squared. And this is basically what is the unit of angular momentum. Okay, so the definition will be, all right, so next lesson we'll continue with a new concept, which is angular momentum, all right? So until then, keep practicing and make sure you do the homeworks that I just assigned for you. Till then, stay safe and keep practicing. Assalamu alaikum.
سەرکەوتنە بەهایبوونە هەڵکشانت بەرەو لوتکە بەرهەمی ماندوو بوونە پیرۆزە هەر لێت پیرۆزە سەرکەوتنە بەهایبوونە ببزوێنە خوچەی لێو ببورژێنە خەندەی شادی لە پێشوازی وا ڕۆژی گەشت بخوێنە بە ئازادی ببزوێنە خوچەی لێو ببورژێنە خەندەی شادی لە پێشوازی وا ڕۆژی گەشت بخوێنە بە ئازادی لە پێکەنە بە دڵشادی وكان ونديش تا منزل وشي